Hi Bobcats. In this video we're going to take a look at something called resonance structures. When resonance structures are appropriate for describing the bonding in a molecule, it's a pretty good indication that the Lewis structure concept for representing the molecule is not quite the whole story. We're kind of pushing the limits of what Lewis structures are good for, and so there's a more complicated story that will unfold in the next couple of chapters. We're typically going to need something called molecular orbital theory to have a better understanding of the bonding. However, Lewis dot structures can be drawn with a paper and a pencil and a periodic table, whereas MO theory requires computers, and once you see the correlations between MO theory and Lewis dot structures, you can make that leap of faith from your Lewis dot structure to what the MO theory is likely to predict. Our objectives are to recognize that Lewis dot structures are not quite the whole story for some molecules, and that will give rise to a description of the bonding that includes delocalized electrons. And we need to be able to draw these multiple resonance structures that follow the octet rule when appropriate. There is sound experimental evidence that supports the idea that the Lewis dot structure descriptions are not quite complete when it's possible to draw these things called resonance structures, and it's largely based on bond length measurements. If we have a single bond versus a double bond versus a triple bond between the same pair of elements, it turns out that the single bond is the longest of those bonds and the triple bond is the shortest. The more bonds you form, the tighter the two atoms get pulled in towards each other. So keep that in mind as we go through some of this information about resonance structures. Single bonds are the shortest, double bonds are kind of intermediate, and then triple bonds are the longest, because that experimental data is going to show that some of our Lewis dot structures aren't the best representation. All right, so what are these resonance structures? They are equivalent Lewis dot structures that differ only with where we are placing multiple bonds and lone pairs. And when it's possible to draw these resonance structures, it's an indication that the Lewis dot structures don't represent the whole story of the bonding in these compounds. And we'll talk about something called a resonance hybrid, where that resonance hybrid is a mixture of the good resonance structures that we can draw and is a bit closer to the real molecular ion than any one particular resonance structure. And it's going to bring up this idea of delocalized electrons. For the most part, we think of with a covalent bond that the pair of electrons that is shared is physically located in between the two atoms that it's bonding. But with delocalized electrons, you might have a pair of electrons that is able to move around 3 atoms or even more atoms in a molecule. And so when they're not stuck between 2 atoms, we refer to those electrons as being delocalized. The nitrate ion is a good opportunity to talk about resonance structures. If we were to do the valence electron count, we're going to have 5 electrons from nitrogen plus, let's see, there are 3 oxygens, each with 6. And then because of that -1 charge, we have to add 1 more electron in. 6 times 3 is 18, plus, let's see, 5 plus 1 is 6. So 18 plus 6, that's going to give us 24 valence electrons. And I wanted to have a good structure to work with for this next argument, so I went ahead and drew it. Nitrogen is going to be in the middle. The 3 oxygens are arrayed around it. When we place those 24 electrons into this structure, we start with octets on the outside atom, and that's the point at which I'm at with this structure. Each one of these oxygens has an octet, so 8 times 3 is 24. We have used up all of our valence electrons. So the next step in drawing the structure would be to shift one of these lone pairs on oxygen to be a double bond with nitrogen, because right now nitrogen's short of an octet. It only has 6 electrons. But we have 3 atoms to choose from. We could possibly start with this left-hand oxygen and shift in a pair of electrons, or we could use the top atom and shift in a pair of electrons, or we could use this right-hand atom and shift in a pair of electrons. Any one of those 3 shifts would give us a perfectly fine Lewis dot structure. So we could have a structure that looks like this, where the shift has come from the top oxygen, or we could have a structure that looks like this, where the shift was done with the right oxygen, or we could have a structure like this, where the shift was done with the left-hand oxygen. So which one should we use? Well, it turns out that none of these quite match the experimental data. If you look at all 3 of these structures, they are indicating that we have 2 single bonds and 1 double bond between nitrogen and oxygen. The double bond should be shorter than the single bond. And if you take the nitrate ion and you use spectroscopy or X-ray diffraction or something that can measure the length of the nitrogen-oxygen bond in the nitrate ion, it turns out there's only 1 bond length, and it's a little bit shorter than a single bond and a little bit longer than a double bond. So one way of trying to explain this is to say that these 3 Lewis dot structures are in resonance, which we will indicate by putting these double-headed arrows connecting the structures. And we'll say that all 3 of these structures are contributing to what the real structure looks like. Sort of like a, let's see if I can get this right. I think it's a horse and a donkey. When they mate, they produce a mule, and so the mule is the hybrid. It has characteristics of a donkey and it has characteristics of a horse, but it's not like it bounces back and forth from a horse to a donkey. A mule is just a mule. It has characteristics of both. Well, in this case, with our resonance hybrid, what we'll say is that the real structure has nitrogen in the middle, and then it has 3 oxygens. And when we measure those bond lengths, the way we'll represent them in this Lewis dot structure is with a dotted line for that extra bond. That extra bond is actually spread out over all of these atoms. The electron pair that makes up that extra bond is delocalized over this entire ion. It's able to roam over all 3 oxygens and the nitrogen. And so this description here with the 1 1/3 bonds in each position is a much better representation than any one of the resonance structures. So this guy up here is our resonance hybrid, and it is in between all 3 of these resonance structures. And the bond length between nitrogen and any one of the oxygens in that resonance hybrid is the same. So only 1 bond length, which matches experimental data. When you have a compound or an ion that requires drawing a set of resonance structures, the Lewis dot structures are an incomplete description of the bonding in that molecule. We're probably going to need to draw on delocalized electrons to explain it a little bit better. And so at this point in our study of this phenomenon, if you have the opportunity to draw multiple resonance structures that all follow the octet rule, where all you're doing is shifting around the location of double bonds or triple bonds and lone pairs. You should draw all of them and indicate that you'll have a resonance hybrid, which has contributions from all of those resonance structures.